everyone, I'm Dr. Munji, and today's video is going to cover bending stress. Alright, so let's start with a quick outline. First, we're going to cover beams, which are one of the most important structural members. Then we're going to cover the flexure formula and do a very short, hopefully short, derivation. We're going to go over an example problem, and then I'm going to leave you with a practice problem so that you can try this on your own. Alright, so let's start with beams. What is the actual definition of a beam? We've heard the term beam kind of thrown around often, but I hope you remember the actual definition. So I put it here for you. A beam can be defined as a long, slender member that supports loading applied perpendicular to its longitudinal axis. What does that mean? Well, if this is the longitudinal axis of a member, a beam typically supports loads applied perpendicular to this longitudinal axis. So you see how this is perpendicular, it makes a right triangle. That's typically how we define beams. These beams carry a lot of gravity load, and usually that's why gravity load is coming from the top, and these gravity loads are applied perpendicular to the member. So that is the definition we have of a beam. These beams are generally long and straight, right? And they usually have constant cross-sectional area. So typically for civil engineering design, we don't have too many beams that have varying cross-sectional area, okay? We like to keep this simple for construction purposes and for design purposes. We often classify beams by the types of supports that they have. For example, as you can see here, I've labeled a simply supported beam. What does that mean? It means that it's supported by a pin on one side. We usually denote a pin by this little triangle, and a roller on another side, which I'm going to draw as a little circle. We also have a cantilever beam, which means we just have one fixed support on the end, and then we have a free end on the other side. We also have something called an overhanging beam, and that's when we have a pin support, and then the roller is not quite at the end of the beam, but it's still supporting that vertical direction somewhere else at the length of the beam. Okay? These are just a few examples here of the most common ones that we use in engineering practice. Why are beams important? So they're one of the most important structural members because you'll find them in so many different structural applications, from the floor of a building to the deck of a bridge or the wing of an aircraft even. You could even think of a bridge as just a really big beam, right? It's just a long, slender member that has to carry gravity load. So beams are very, very important, and that's why we're going to spend this whole video, and you spend a lot of your class time learning about how to design beams appropriately, okay? And I even put this on here too. You can even think of some of the bones in your body behaving like beams. So sometimes when you're in mechanics of materials or structural analysis, you want to think about how your bones are moving, right? You have joints, you have supports, and those actually can kind of emulate beams as well. Over the flexure formula, okay, which is really important for beams. So I'm actually going to start here by drawing a beam. Okay. Now, there's a very detailed derivation for the flexure formula. I'm going to try to simplify this as much as possible so that we don't have to get into too many of those kind of nitty-gritty details, okay? We just want to get the general idea and then refresh your memory on the flexure formula and apply it to a problem today. So let's say that this is a beam, okay? And we can say that this is actually, in the real world, a 3D system, right? So we have a 3D beam here. And this beam has some length, L, right? And we have three axes in the 3 dimensions. So we're going to have this axis here. We're going to call this the x-axis. And then we have this axis here, the face of the element. I'm going to call this the y-axis. And then you can kind of see going into the page right here, we have the z-axis, okay? And what happens here is we're going to say we have some applied moment about that z-axis. So I'm going to try my best to show you. It's rotating around this z-axis. On either end of the beam, we have a moment in the z direction. Okay? And what we're going to do now is we're going to make a cut along this beam. Okay? We're going to make a little cut. We love making cuts and deriving things for those little teeny tiny differential elements, and then we expand it to the entire length of the beam by doing what? By integrating, right? So we're going to make a little teeny tiny cut. But before we make this cut, let's kind of see how this bending along the z-axis affects this beam. So let's remember what happens here. I'm going to go back to 2D. When we apply that moment, well, that wasn't 2D. I'm going to exaggerate this, of course. This is not, this is a very exaggerated swoop there, but what's happening is this beam is bending, right? This beam is bending. And we have something called, well, I'm going to wait, actually. We have this axis in the middle. This is the middle axis, right? As this beam bends, what happens to the top fibers of the beam? That top length of the beam gets shorter, so it goes into compression. And the bottom of the beam gets longer. It's in tension. That's when we apply this moment, right, in this direction. And we have this line that I drew that I was going to tell you what the name was, but then I decided to wait. This is called the neutral axis, or abbreviated as the NA. Okay, what is the neutral axis? That is the axis. It's the point where the length remains the same as the original length of the member. So it's neither in tension or compression. Has zero change in length. Okay. So now let's come back to our little cut that we're going to make over here. And let's zoom in on this teeny tiny differential element, or this little cut that we're going to make for now. We'll make a little, just a little cut to see what's happening. Okay. So let's say we have a cut. I'm going to show you the face of that here. And let's say that the length of this cut, just some tiny length, delta x. Okay. We know we have the neutral axis in the middle there, which is that axis that's on the middle. Right here. Okay, let's say this is the NA. And we also, this is prior to loading the beam, okay? So that's why the neutral axis and delta x are the same. This is before loading. So this is before we're bending the element, before there's tension, compression on the top. This is just before loading, okay? This is basically what we're dealing with, right? We just have delta x and we have the neutral axis there. What happens, seems like I don't have enough room. Let me make this a little smaller. What happens okay, after loading this, I'm going to draw kind of the difference now, what's happening to load the element before and after. So I'm going to try to show you this exaggerated curve again. Oh. This is the same element I drew up there. Okay, but now we're bending it. Remember, we're bending the element. So what's happening now is I'm going to draw that same reference, that neutral axis. What's the length of the neutral axis if it doesn't change? It's still delta x, right? What's happening, though, is we're curving the element. So what we have is we have kind of this like arc, or this circle, and I'm going to pull this down again. I keep not giving myself enough room. Do it over here. Okay, this is a circle. There's kind of like this is an arc. It kind of, you can see the circle that's forming, and we have this point here, which we call the center of curvature. What that is if we're going to make an entire circle, that would be the center point, that center of curvature right there. Okay. Now, what we're going to do is we can kind of see this forming. All right. We have this like little piece of an arc here. Okay. And we're going to define a value. Okay. We're going to define a value called C, right? I'm going to measure this value C from the neutral axis up, okay, to the very, very top of my element, the topmost fiber of my element, okay? So what is C? C is equal to the extreme distance from the neutral axis to the outer side of my element. So the distance from, I'm going to call the neutral axis the NA, to the outer side, or that extreme fiber, right? This can be to the top or to the bottom. I'm going to say it's to the top. Okay, to the top of the element. And remember that this is before loading here. This is after loading. Okay, that's after loading. So remember, the neutral axis here in the middle remains unchanged in length. There's no change at the neutral axis. Okay, and now we have the center of curvature. We have this value C, this distance from the neutral axis to the topmost fiber, which we know, if we're bending in this direction, is in compression, right? So now what I want to do, okay, I want to kind of skip a few steps because I want this to be more of a refresher video. I don't want to go into a detailed derivation here. But what we can do is we can calculate the normal strain. Okay, we can calculate normal strain from any distance from the neutral axis, right? So what is strain? Remember, strain is epsilon. And we're going to say that this is some distance from the neutral axis divided by rho, okay? I've skipped a few steps in the derivation, but we're going to say that this is negative y divided by rho. Where did I get y and rho from? I'm going to show you. Rho is defined as my radius of curvature. Okay, what is that value? It is the distance from the neutral axis to the center of curvature. This is my rho. And now what is y? Y is the distance from the neutral axis to the point I am trying to measure the stress at, okay, or the strain at. So y is any distance from the neutral axis to the point I'm trying to measure the strain at. Rho is the radius of curvature, okay? Now, we know that the normal strain varies linearly across the cross-section of the element, okay? So I'm going to quickly draw the cross-section of the element here. Okay, I'm going to show you the deformation. I'm going to show you the strain profile, and then we're going to get the stress profile so that we can actually get to the Fletcher formula. Okay, now, the deformation of the element, remember, we have the top of the element in compression. We have the bottom of the element in tension. If I connect those two, I get this. So we have compression at the top, tension at the bottom. And remember, this is our neutral axis here in the middle. And that's where we're rotating about. We're putting that moment about the neutral axis. Okay, that's where the applied moment is. Now, for our strain profile, at the top, we have a negative strain because this is in compression. Okay. The bottom, we have a positive strain. And again, we're going to connect those 2 points. Okay. What is my C value in this case? Remember, my C is the value from the neutral axis to the very top. And what is Y? Y is any measurement I want. It can be half of C, it can be 3/4 of C, whatever. Y is any distance from the neutral axis to the place that you're interested in getting the stress or strain at. Okay. Last one now is my stress profile. What I have here, I have tension, so I have arrows pulling in this direction. Right, this is the stress profile. And at the top, I have compression, so now I'm going to have arrows pushing in this direction. Okay, my sigma max is here at the top for my compression. And what I have here is I'm going to put this in a different color. I have my resultant here in compression. I have my resultant here in tension. And this is the moment arm between the two. This is a couple moment. Or a couple. Excuse me, this is a couple, right? Okay. So now, this is the moment that's applied, right? This is my applied moment, M. What I have here, I can use similar triangles. I'm also going to skip a few steps, but I do want to show you this where I'm getting it from. The moment is equal to either T times the arm or C times the arm, right? That moment arm. This is a couple, okay? And we're also going to use good old Hooke's law. What is Hooke's law? Sigma, stress, is equal to modulus of elasticity times epsilon, which is the strain. I'm going to plug everything in that I have solved for here. I'm also going to use, these are what I'm using. I'm also going to use similar triangles. And if I plug all of that in, I'm going to end up with the flexure formula, which is sigma is equal to, okay, my over I. Okay, what is I? I is the moment of inertia. I'm going to highlight this. So I'm actually going to add another page here. Let's come in here. So let's write this out. The flexure formula, we have sigma equals my over I. And if I want the maximum, what value am I going to put in for the y? It's going to be that c value, the max distance. Okay, so now we have derived almost, not, maybe we skipped a few steps, but we have the flexure formulas. Okay, just to go over what each of these values are. So m is the moment, y is the distance from the NA to the point of interest, and I is the moment of inertia. Only difference here between the sigma equation and the sigma max equation is this guy right here, C, right? And this is just the distance from the NA to the outermost point. Can be top or bottom. Okay? Now that we're done with that, let's go ahead and try an example. Okay? So we have a simply supported beam that has a cross-sectional area shown, and we want to determine the absolute maximum bending stress in the beam. Okay, so we need a few things for this beam. We're going to keep going. So we have 5 kilonewtons per meter times 6 meters to get the resultant of 30 kilonewtons, which means we have reactions of 15 kilonewtons on each side. Why do I need that information? Because if I want to get the absolute maximum bending stress, that means sigma max equals MC over I need M, right? I need M, I need C, and I need I. I need to get the moment. How do I get the moment? I have to draw the shear and moment diagram, okay? So we're going to go ahead. I'm going to quickly draw the shear and moment diagram because you do have another video that goes over in detail how to draw a shear and moment diagram. So I'm not going to cover that as in-depth, okay? I'm going to go over it quickly. So here is my shear force diagram. Here is my bending moment diagram. V is in kilonewtons. M is in kilonewton meters. For the shear, some blue. I'm getting pushed up to the 15 kilonewton point, but then I have a linearly decreasing load for that constant distributed load, and then I get pushed up by the last 15 kilonewton support, and that is my shear diagram. Okay, moment diagram corresponding to the shear diagram. I start at 0, I end at 0, and I have kind of a parabolic shape. What is my max moment? It's just equal to the area under the curve of this portion, which is going to be 1/2 times 3 times 15, right? This is 3, which gives me 22.5. Okay, so my M max is 22.5 kilonewton meters. Okay, that's internal moment and it occurs at 3 meters. Now, I'm going to go ahead for this shape here. I'm going to copy it. And we're going to come back down here, and we're going to calculate the moment of inertia for this I-beam. Moment of inertia. So, by symmetry, the neutral axis acts at the center of that system, right, the center of that member, or that cross-section. So what I'm going to do here, I'm going to use the parallel axis theorem. I hope this rings a bell. The parallel axis theorem is the sum of all moment of inertias plus AD squared. Okay? And what is the moment of inertia for a rectangular shape? 1 over 12 BH cubed. Okay? I'm also going to go through this a little bit quickly because this should be a review for you. So we're going to have 2. Why am I putting 2? I'm going to do the top portion. I'm going to call this 1. I'm going to call this 2. And this middle portion 3. So I'm going to add 1 and 2 together now. I'm going to do the moment of inertia for 1 and 2. So I'm going to put 1 over 12. What is the base? It's 250 millimeters, so it's 0.25 meters. What is the height of those sections? It is 20 millimeters or 0.02 meters. Okay, but now I need to add my AD squared because the central axis of those two members does not lie on the neutral axis. So I need to bring their moment of inertia to the center, and the way I do that is by adding AD squared. So what is the area of the two shapes? Well, it's 0.25 times 0.02. What is the D? D is the distance from the center of those flanges to the neutral axis. I'm going to zoom in and show you this once quickly. Distance from the center of this flange. Get a thinner pencil here. To the neutral axis. This is my D, and you can see that it's the same. This is D2, D1, right? It's the same. Okay, that's how we calculate D. That's this value here. So, what is my D value? I get 0.16. And that is the flange. Now I'm going to add 1 over 12, base of the web, which is 0.02, times height of the web, 0.3 cubed, and I get a moment of inertia of 301.3 times 10 to the negative 6 meters to the fourth. And now I just need my C value. What is my C value? It is the distance from the neutral axis to the very top fiber for the maximum value there. And that is going to be 0.17. Basically that 0.15 plus the 0.02, we get 0.17. So converting it to meters. And we're ready to plug in my sigma max here. Equals MC over I. What was our M value? 22.5 kilonewton meters. I'm going to change this to Newton meters, so I'm going to multiply it by 10 to the third. And then we're going to have the C, 0.17 meters, divided by my I value of 301.3 times 10 to the negative 6 meters to the fourth. And I am left with 12.7 megapascals. And that is final answer. So that is how you apply the flexure formula to solving for the stress in a beam. Okay. Now you can try this practice problem on your own and see if you're able to solve for it. I'm Dr. Mungie, and I hope you enjoyed this video.